Hello, welcome back to our video series on fluid mechanics, where we just do the bare essentials of fluid mechanics, hopefully enough to help us understand the basics of it and help us understand, our lecturers, what they're talking about. So today we want to continue with this topic called dimensional analysis. Now, in our last video, we were discussing frictional losses. You see all that we have done, and we have concluded that this k value, which represents our dimensional losses, are in fact a function of some fluid property and pipe dimension, etc., etc. We just don't know what this excuse me yeah, we just don't know what these are. Therefore, we need to start discussing. So remember our energy equation, and then we try putting it in this form, in a per volume basis. And of course, we know that this becomes K half rho V at B square. And that is all. Next question. It's like, how do we find this k value? Yes, and we were discussing before, we might have lots of experimental data in here, and then we also want to find our actual k value. Yeah, we have lots of experimental data here. We wondering whether this thing is actually our k value, and we realized that that's not the case, because if that was your k value, then it kind of doesn't make sense, because then you have the case that, okay, whether I pump oil or pump honey or pump thick tar through your pipe, your frictional loss coefficient is going to be exactly the same. Then that kind of makes you want to scratch your head. It's like, hey, does that make sense at all? So obviously, yeah, that does not make sense. So today we want to ask what affects k, and then how can we develop correlations between those variables and k. So if the fluid viscosity, that means how thick the fluid is, if that's going to affect k, can we find a formula? How that affects k, along with the pipe length, etc., etc. So just a quick introduction on viscosity. Tau equals to mu partial u partial y. So what are we having here? This viscosity. So mu is this viscosity, yeah. Though I just pulled a formula out like that you've never seen before, don't worry, we're going to discuss each of these terms slowly. So again, let's say we have a fluid, and it's at a wall. Okay, so we have some thick blue colored fluids, yeah, we like to color them blue because it's like water. And then, okay, let's say we apply a force in this direction to the top layer of the fluid. So we apply this force to the top layer, and I'm gonna color it a different color, yellow. It looks like shell now. Anyway, it's gonna cause the top layer to move, right? So if the top layer is going to move into the right, and the top layer is going to move to the right, and we're not going to exert force on the bottom layer. But because the fluid is sticky, the layers of fluid will have forces acting between each other, and the top layer will start pulling the next subsequent layer forward, though by slightly less, because there is a force if let's say you have, okay, let me divide this out. You have the top layer, this layer, and the next layer. Okay, so let's say we can treat the top layer like a block. So we push it forward this way, and the top layer of liquid goes forward this way, and it's going to exert a force. This top layer is going to exert a force on this layer, and then this layer says, hey, I want to go forward. But in doing so, it's also going to pull the next layer underneath it. And by Newton's third law, the next layer underneath it is going to say, hey, don't move so fast. So this next layer is going to move forward, but slightly slower, and so on and so forth. So we have a velocity profile, something like that. And this is the picture. Okay. Now, this top force that we are applying, we can put it in terms of a per unit area. So tau equals to a stress, a shear stress we call it. Shear stress is merely force per unit area, except it is a vector. Okay, so tau is shear stress, it is a vector. It's in the units of pressure, so the units are usually pascals or gigapascals or psi, etc, etc. And it's going to be a vector because pressure is usually a scalar quantity. Tau is a vector quantity, and it's pulling, and that's how we describe the force that's acting on this fluid. We call it in terms of stress, and this stress is called shear stress. Why is it called shear stress? Because the arrow is pointing in the direction of like it's parallel with the length of the fluid. There are other kinds of stresses too. I'm not going to talk about them in this video. Now, how do we measure the fluid's response to this stress? We look at the variation of the velocity as it goes down. So that's why we have this du dy, or partial u, partial y, where we just get this velocity gradient of how fast the fluid is moving as we travel up and down from here to here. So this is the y-axis. So I'm going to click a lot here. This is the y-axis, and this is where u is going. Alright, so if the fluid is thicker, then you expect the gradient to be very steep. Why? Because the fluid is going to, wait, no, is it fluid? Yeah, if the fluid, okay, let's put it this way. If the fluid is more sticky, then the top layer is going to exert a large force on the bottom layer, and it's going to cause the bottom layer to move forward more. So let's draw it for maybe a slightly stickier fluid. Okay. So for the same force, maybe the velocity profile is slightly, skewed, so that the variation in the variation in the velocity as it goes from the top to the bottom is slightly different. It's going to be a bit flatter. Okay. So if this goes down, if this is lower, then this will be higher. This mu will be higher for the same shear stress, and that is, this mu is the constant of proportionality. We call it viscosity. Okay, mu equals to viscosity. And what are its units? What are its units? Well, this in terms of pascals, and this is okay. Let's look at the units. Units. It's a speed, so it's a length per time. Divide by length. and that will give you time per unit time inverse, and this is in pascals, which is in, let's say, force is mass times acceleration, so it's mass times acceleration, so meter per second squared, or length per time squared, and then that is divided by area, so it's divided by L squared, and that's how it works. So if we take this, we're going to get mass length time to the -2. That's what the units of pressure are like. And okay, this should be -1. And then let's do viscosity. Viscosity is a mass times length times time inverse, because if we cancel out, look at the right hand side, it's a t to the -1. If we divide both sides by t to the -1, we will get t to the -1 here, and we will have this. That is the unit of viscosity. So that helps us to determine how sticky the fluid is. So you guess that this K value is going to be some function of the fluid properties, the pipe dimensions, blah 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 blah. Okay, so let's start from the most simple thing first. Let's start from the most simple thing. We want to compare pipe sizes. And we'll want to make some guesswork. Okay, so we'll have two pipes. One, they're exactly the same cross-sectional area and shape, except one is longer than the other. Now, how is it going to vary? Okay, and we're going to have fluid here and here. I'm going to paint it. Yeah. So we have one short pipe and one long pipe. There's a short pipe and there's a long pipe. Which one do you think will have more friction? Well, if we talk about let's say even a car or walking, we'll notice that the work done by friction equals to the force times distance. So let's say we have friction work done equals to force times distance, and assuming the force is constant, so the friction work done is proportional to a distance. So we could postulate, we could guess. Yeah, we could guess this is the same for fluids. Alright, so that's one clue. Maybe K is proportional to length, the pipe length. Alright, so let's take a look at the next comparison, because this is probably the most straightforward. Let's take a look at another scenario. Delete this, and I'm going to delete this. You'll have one small pipe, one big pipe and one small pipe. Now, how is the K going to vary between these? So I'm going to put a box again. I'm going to paint it blue, and we're going to have these two. Same length, but a thick pipe versus a thin pipe. Now, just imagine with me, you have a straw. You have a thick straw and a thin straw, and you're drinking the same drink. If you have a straw that has such a small, volume, is it easy to suck? Well, not necessarily. Usually a thick straw will be easier to drink from as compared to thinner straws. Why is that the case? Okay, let's think about highways. Let's think about highways. Or expressways, however you call them. If you have a 3-lane expressway or 3-lane highway, we know that let's say here you have an exit, right? Here you have an exit, and usually the lane here will slow down. Well, these are the faster lanes, okay? And this is on a, of course, if you are on a right-hand drive. If it's a left-hand drive, you go the other way. Yeah. But anyway, you have an exit. This lane will slow down. This lane will slow down, but these are fast. These are fast lanes. Okay. That is if the drivers are driving right. But you could think about traffic on this versus traffic on a 6-lane highway. Yeah. Would it be easier to travel from, let's say, point A to point B, somewhere here, on a 6-lane highway or a 3-lane highway? And the answer is pretty intuitive. Of course, you want more highway lanes. So for the same length, you kind of want more volume, so to speak. This pipe volume should be bigger. So we could guess K is proportional to 1 by volume. And of course, when this pipe expands, the volume increase, so we expect the K to drop. Now let's say we also have compared these two surface areas. These two surface areas. What surface area do I mean? So I'm going to delete all of this. These two surface areas. I'm talking about the curved surface area here of the pipe. So imagine the curved part of the curved part of the pipe, let's say. So all these are going to have some form of surface area. Okay. If we were to keep this pipe volume constant, but we increase the surface area it's being exposed to, how would it change? So let's say we have a pipe. Okay, two identical pipe with the same volume, or rather, let's put it this way. I have a circle, this is a cross-sectional area, and then I have a star. Then I will paint both of these. Let's say these are the same volume inside, but here the star we have more surface area. Okay, so I'm going to copy and paste over. Now, which one do you think is going to have more frictional force? Is it the one with less surface area or the one with more surface area? Well, if the shear stress, let's say for a given flow regime or flow situation, this shear stress is the same, the force exerted on the fluid is proportional to the area. Can you see here? Shear stress is the force per unit area. So if you increase the area, the surface area, the frictional forces will increase. So let's see. We should also guess K equals to A. Alright, so these are some of the important, probably the most important pipe dimensions. You talk about pipe length, you talk about surface area, and then you talk about the pipe volume. So how can we put this all together? So we'll have, okay, K equals to, or proportional to, area divided by volume, then you times the pipe length. Okay. Now, let's say we have this area by volume for, let's say this part, this circle. So area, the curve area will be 2 pi r L. That's right. 2 pi r L will be the curved area. That will be the diameter of the circle, and then we'll multiply into the pipe length. Oops. And then we will have the volume, which is equals to pi r square L. Now, if we divide A by V, what will we get? A divided by V. What do we get? We will get 2 pi r L over pi r square L. That will get 2 over r. You can check the pi and the pi cancels out, the L and the L cancels out. There will be a 2 on top, and the r over r squared is just 1 over r. So we'll find this pretty interesting result, 2 over r. If not, if we use the diameter, we'll get 4 over d. Okay. And if we take a look carefully, this area and volume, and we measure the ratios, okay, let me just underline these things. Okay, the surface area to volume ratio is the same as 2 pi r L over pi r square divided by pi r square L. And what do we notice? This is actually the same as the 2 pi r is the circumference over cross-sectional area. So we can also write it as perimeter over cross-sectional area. So let's just put XS for cross-sectional area. Alright. And then we will get this following relation for a circular pipe. And then we will get K. We can guess K is related to the pipe dimensions in this manner. There should be an L on top. So the L by D times 4. So K will be proportional to this, or in other words, K is proportional to L by D. Okay, that will give us some clue, but that feels like a lot of guesswork, and you're wondering, hey, is there a more systematic way to do this? Well, we'll discuss more in our next video. I'll see you next time.